So Paul has been working for 5 years before that at Brookhaven National Laboratory, working on timing systems for the electron-ion collider. And today he will present to us updates on the timing distribution, the deterministic timing distribution for AMD FPGA is a topic very hot for our community. So please, Paul, welcome. Thank you.
Thank you for the introduction. And so, good morning. I'm going to talk about some ongoing R&D work that pertains to precision timing distribution using AMD transceivers. I'm going to talk about some of the techniques used to achieve deterministic and repeatable latency, tying them together into a custom protocol. And then I'll get into some ideas for future improvements. So here's an outline of what I'm going to talk about in order. First, an overview of what exactly it is we're trying to do. Then I'll describe a technique to achieve deterministic latency through an asynchronous FIFO for clock domain crossing. Then I'll talk about the details of how to align a high-speed transceiver transmit and receive channels, the clocks pertaining to each, and then tying it all together into a protocol for precision latency measurement of a high-speed serial link and latency control. Before that, just some background about Xlight. It's a US-based startup company working on building a EUV, extreme ultraviolet light source for silicon lithography, and it uses an energy recovery LINAC to drive a free electron laser to generate the EUV light. Here's a rendering of our machine design. All right, so an overview of the timing link. So of course, we want precision timing distribution over bidirectional high-speed serial optical link. And this is leveraging R&D work that was done for the electron-ion collider timing distribution at Brookhaven. It's a very similar concept to the TC-Link from the HPTD, the open core that was developed. There's just a difference in the actual scheme for latency control with this approach. So the main goals is we want 1 picosecond of latency measurement resolution, and we want that 1 picosecond to be repeatable across resets, which is the real challenge. And more of a nice to have is about a 1 nanosecond or sub-nanosecond absolute phase offset accuracy before going in and hand tweaking delays and things. And of course, we want to stabilize and minimize the temperature drift as the temperature of each system or the temperature of the fiber between the systems changes. And I'll talk more about that at the end. And so the key building blocks here are achieving deterministic latency through the FIFOs, and then properly aligning the transmit and receive clocks of each channel. And on the right is a block diagram showing the major components of 2 connected FPGA systems with the optical link between them, where the one on top is receiving an external clock reference that it needs to distribute, and the one on the bottom, labeled FPGA2, is recovering the clock and using it for the synchronous timing link. So first, I'll go into the details of how these FIFOs work. So they're necessary for crossing between the FPGA fabric clock, clocking the user logic, and the MGT channel transmit and receive clocks. So the transmit has its own FIFO and the receive has its own FIFO. And so it's important that the latency through these is deterministic across resets for round-trip link latency measurements or forwarding a link. Really, anytime you need to go receive data on a receive clock domain and then retransmit it to a transmit clock domain. How to do that with repeatable latency is a challenge. So these are dual clock FIFOs. And in this case, the write and the read clocks are synchronous, same frequency, but they have a variable phase, especially across resets. Sometimes it's called a phase compensation FIFO. So the MGT channels in the AMD transceivers that we're using have elastic buffers that provide this functionality, but they come with an inherent 1 clock uncertainty across resets. So instead, the MGT channel can be used in buffer bypass mode to replace the elastic buffer, and we can use our own and instantiate an asynchronous FIFO in the fabric and use that instead. And the reason this is beneficial is because we can precisely control the reset sequencing on the FIFO if it's implemented in Fabric. And we can do this to take advantage of the fact that we can manually phase align the write and the read clocks on either side of the FIFO. So I'll go into more detail about how that's actually done. So here is a more detailed diagram of the FIFO and a simplified schematic of the flip-flops for the reset chain. First, our job is to manually phase align the write and the read clocks, reset the FIFO, set the count to 0. Then we want to assert the write enable with the read enable deasserted. And then a few clocks later, through this flip-flop delay chain, assert the read enable, and then keep them asserted. What this does is it fixes the FIFO level at a known value, and therefore it fixes the latency through the FIFO from D in to D out across resets. And of course, the write enable signal that we delay to the read enable domain has to cross from the write clock to the read clock domain. And that's a clock domain crossing that's labeled in the diagram towards the bottom right. So we can use static timing analysis to ensure that this clock domain crossing is always repeatable across resets, given that we have already phase aligned the two clocks that it's crossing between. So on the transmitter, what does this look like? For the TX FIFO, the write clock in this case is the MGT ref clock, which is forwarded to Fabric to clock the user logic, and that's highlighted in green. And the read clock on the FIFO is the TX user clock coming out of the MGT channel, it's highlighted in red. And so on the FPGA upstream, labeled FPGA1, we want to align the TX user clock with the MGT ref clock on either side of the FIFO before we reset it. And then on the upstream system, we'll adjust the phase of the TX user clock to control the overall link latency. On the downstream system, we just want to align the TX user clock and the MGT ref clock and then leave them in alignment and fix that. So how is this done? Here's a more detailed clocking diagram from the transceiver documentation. So it's really on the right, you'll see the clocking structure of the transmitter side of the MGT channel. This is from a GTH transceiver. And then I stuck it together with the diagram of the QPLL just to show the full clock paths through into the TX out clock. So if you'll notice, the red clock path comes out of the QPLL into the MGT channel through a series of clock dividers and then out to the TX out clock mux. And the green clock path comes in externally as the reference clock to the QPLL. And it also goes into the MGT channel and can be routed to the same TX out clock mux. And these clock frequencies are chosen to be equal for this design to work. And our job is to manually phase align both of these clock paths. And we can take advantage of the fact that the phase offset between them will only differ by a discrete number relating to unit interval steps, 1 unit interval, basically the frequency of the high-speed serial clock. And we can measure the phase between them by reading the delay aligner value that is used in the buffer bypass mode and switching the TX out clock mux between the two clocks and measuring the value for each. And when they're equal, then we know that the two clocks are phase aligned. So we can manually adjust the phase of the TX out clock in the red clock path by overriding the phase interpolator. And so what we can do is just cycle it through one full iteration to shift by a unit interval, then keep doing that and remeasuring until we measure no phase offset between the two clocks and we know they're aligned. So I'll show some measurements from this. So like I said, we're selecting one clock with the TX out clock mux, measuring the delay aligner value, selecting the other clock we want to align to, measuring the value again, taking the difference, and that difference is shown on the x-axis in this plot, and it corresponds to the phase between the two clocks. So you can clearly see the peaks associated with the unit interval steps clustered in the phase difference between the two clocks. And then there's these smaller peaks in between the larger ones that are separated by a unit interval. The smaller peaks are at a half unit interval, and that's an artifact of the fact that in this GTH transceiver, if you see, can I point to this? There's a divide by 2. There we go, right there. So the QPLL clock is actually running at twice the line rate, and it's divided by 2 before being input to the MGT channel. And this divide by 2 divider also has an uncertainty across resets, which causes a half-unit interval step, which for some reason is less likely than the integer unit interval step. But nonetheless, the key idea here is to show that this can be measured accurately enough to know when the 2 clocks are phase aligned, and that's shown by the one peak with 0 offset towards the center of the plot. So this is nice because now we can measure this, and we can ensure that these 2 clocks are in phase by putting some bound on what the measured value can be. And this was tested across 4 physical devices, each at 30 degrees C around room temperature and 60 degrees C at hot. And all of the data is plotted here, so it shows it's important that none of these peaks in this distribution smear into each other, showing that this can actually be measured with certainty that the phase has 0 offset, knowing which unit interval the dividers are at. So with this measurement, then we know how to align these 2 clocks of interest, and we still need to properly constrain the reset path of the FIFO that's implemented in Fabric. So here's a simplified diagram showing the same clocks from the previous diagram, but the MGT channel is shown in the dotted line in the middle, and the asynchronous FIFO that's in Fabric is shown off to the right, just to include the full data and timing paths. And you can see the green clock path goes to the launch flip-flop, and the red clock path that we just aligned to it goes to the capture flip-flop, and that's your clock domain crossing. And the timing diagram above basically shows the internal delays that come from originating from the MGT ref clock to the MGT ref clock going to Fabric, and then the MGT ref clock going through the whole TX out clock path to the TX user clock. So now that these are aligned, we know the delay between them, and we can properly constrain this by just putting a static delay from between these 2 clock paths. And we'll pass timing analysis, and this will be valid so long as these clocks are dynamically aligned. So once the clocks are aligned, we reset the FIFO, and then we know that the latency through it is deterministic. And then afterwards, the clock phases can walk with respect to each other, and the FIFO level will rise and fall to accommodate that. But we know the initial latency as a starting reference point. That's very important. So that's on the transmitter. And now it's a similar case for the receiver, but instead the write clock is the RX user clock, and the read clock is the MGT ref clock to read the received data into the user logic. And the alignment procedure is slightly different, but the concept is the same. We want to phase align the RX user clock and the MGT ref clock on either side of the FIFO. And this is done on the upstream system, the one in the top diagram, by adjusting the total round-trip link latency to change how long the clock takes to traverse the whole link and come back. And on the downstream system, the alignment is a little different because it's recovering the clock. So it'll take the RX user clock, and we want to manually align that to the recovered clock that goes out of the chip to an external jitter cleaner PLL, back into the MGT ref clock. And if the user clock and the recovered clock, shown in red and blue, if those are phase aligned, and it's sent out and back in as MGT ref clock is also phase aligned, then the 3 clocks are aligned, and we've achieved our goal on the downstream system. So a little more details about this. Here's the same clocking diagram, but for the receiver side, and the QPLL is the same. It's shared between the transmitter and receiver. And so the RX out clock PCS is the frame clock for received data words. MGT ref clock is the external reference clock for the user logic. And so we want to align RX out clock in red and the RX recovered clock, which is in blue. So naturally, these, and after a reset, have some unknown phase because they go through different divider paths, but conveniently they'll only differ by a discrete phase because they go through dividers. And so this can again be measured by reading the delay aligner and adjusting the phase using the RX slide PMA, which this shifts the RX out clock PCS, the red clock, in steps of 1 unit interval. And then we can keep doing that until we measure it to be in alignment with the blue clock, the recovered clock. And once that's done, those 2 clocks are aligned, which is great, but we've thrown out the alignment of the actual RX out clock with the received data frames. So to realign to the received data, we can manually phase shift the phase interpolator, which shifts both clocks in unison and keeps them in alignment, and then realigns to the actual data being received. So a little bit more involved, but it's the same principle as the transmitter. And here's some measurements on that. And so we measure the average delay aligner value, and you can see the spacing. Here's just 2 peaks shown. There's a little bit more spread than there is with the transmitter, but still there's clearly discernible bins of phase unit interval spacing. And again, this was tested on 4 different devices at room and hot temperatures. And in this case, 1 unit interval is 125 picoseconds. So again, now these 2 clocks are aligned on the receiver, and we have to go and properly constrain the reset path for the FIFO. And so on the upstream FPGA, which is distributing the clock, the MGT-ref clock in green is fixed by the external reference, and the RX recovered clock is changing depending upon the round-trip link latency. So this is manually controlled using the transmitter to delay the transmitted data, which controls the round-trip link latency, and then we can use that to align the receive clock. And so again, we define a static delay from the RX user clock to the MGT-ref clock domains, and then we pass static timing analysis, and we ensure deterministic latency of the FIFO after reset. So putting this all together for a latency measurement and control algorithm, we have the upstream system transmits data frames in phase with the reference clock. The downstream system recovers it and uses it for the fully synchronous link to retransmit data. And what we want to do is measure the round-trip link latency from the upstream system and ensure that it's an even integer number of clock cycles. So the reason for this is if you measure the round-trip link latency and it's an odd number of clock cycles, the downstream system is aligned with a falling edge instead of a rising edge of your clock. So we want the one-way link latency to be an integer number of clock cycles for phase alignment. And so the way this is done is the upstream system measures the RX phase interpolator here, and then it controls the TX phase interpolator, and we want them to be equal and opposite to ensure a constant one-way link latency. So if you only correct the TX phase interpolator, keep the RX phase, the round-trip phase in phase, you'll overcorrect because you're keeping a stable round-trip link latency, but we really want the one-way link latency to be constant, so keep the link symmetrical. And I have a better explanation of this coming up. So here's the procedure for the link initialization. First, on the upstream system, we align the TX user clock with the reference clock. And on the diagram on the right, the step 1, you can see the dotted line represents the absolute phase reference being distributed that we want to align to. So initially, the transmitter on the upstream system is aligned, and all of the other clocks in the downstream system and the receiver are not. So step 2, shift the clock so that the receiver on the upstream system is aligned and initialize the FIFO. Then finally, control the TX and the RX phase interpolator values to be equal and opposite, so you can see they're spaced from the dotted line in equal spacing. And then that causes the downstream clock to be aligned to the phase reference of the upstream clock, a symmetric link latency. The caveat to this is the phase interpolator values only have a maximum range of a unit interval. So in this case, 125 picoseconds, and we want more measurement range than that. And so what you do is, the trick is to unwrap the phase interpolator value. So reset it to 0 at a known 0 phase offset, and then just keep track of every time it rolls over from 127 to 0, keep counting to 128 and so on. Same thing in the negative direction. If you go from 0 to 127, just go to -1. Turn it into assigned numbers so you can keep track of larger phase offsets. And do this for both the transmitter and the receiver phase interpolator measurements. And of course, so the absolute timing accuracy is limited by how symmetric the link latency is in each direction. So more latency in the downstream direction cause a delayed clock on the downstream device. More latency in the upstream direction will cause an advanced on the downstream clock. And so to keep this constant, there are certain tricks you can play. You can use bidirectional SFP modules to transmit different light wavelengths in each direction with the benefit of using one fiber for the bidirectional communication. And this comes with the problem that both light wavelengths that are going in each direction propagate at different velocities caused by the dispersion in the fiber. And so instead, it would be nice to be able to communicate in both directions using the same optical wavelength. And this could be achieved using an optical circulator connected at each end, which with the circulators connected to each other with one long fiber run. So this way, the light wavelengths have the same dispersion in the fiber, and the link latency is well matched. So of course, there will still be offsets in the actual frequencies being transmitted, just because of the SFP transmitters could have some variation over temperature. But it'll be closer than these bidirectional SFP modules that explicitly transmit on different frequencies. So here I have an animation of the process, which hopefully clears it up a bit. And then I'll step through this. And it shows a perturbation in the link latency and how it's corrected if the fiber gets hot and the latency increases, or cold and decreases. So initially, like I said, align the transmitter clock with the reference clock, and then reset the FIFO, shift the clock so that the receive clock is aligned, reset the receive FIFO, and then ensure that the delays are matched, opposite and equal. And then the downstream system clock becomes aligned. And then if the fiber heats up and the latency increases a little bit, you see the receive clock advances, and that's corrected by advancing the TX clock to match. And then same thing, it cools back down, and it corrects. And then if the link latency decreases further, same thing, measurement and correction, and so on. So here's some more information about details. I couldn't get into everything here, but this is the main idea of what we're trying to do. So I'd be happy to answer any questions that anybody has.
Thank you very much, Paul. Do we have any questions, please?
Hi, and thanks for the talk. So you said that the absolute timing accuracy is dependent on the asymmetry of the setup. Do you have rough numbers on how much it is? I mean, of course, it depends on the device. Like, how big is it? Is it in order of picoseconds, tens of picoseconds?
It really just directly depends on how asymmetric the link is. So like, for example, if I go back to this diagram, for a long link, it really doesn't depend on the device. It's really the medium. So if in the middle diagram you see the red arrow, if the downstream direction, let's say, has an extra nanosecond than the upstream direction, you'll see half a nanosecond of delay on the downstream. So it's really just your best approximation of the link latency is to take the round trip and divide by 2. So anything other than that, in reality, well, you'll see that equivalent error on phase alignment.
All right, anybody else? In any case, we can take advantage of the coffee break and corner Paul. Maybe just to say something before we thank him again is, do you have friends in high places? How you manage to hack the delay aligner? What he was showing so far was things non-documented. So how did you do that?
These references at the end describe all of that more than I could, or talk to me during the coffee break.
All right.
Yeah.
Let's thank Paul once again.
Thank you.
And we'll have to be back at 10:45. Yes, 10:45. Then see you for the second part of the same session.
Oh, yeah. Thank you.
I knew, but I wanted to mention it.
Oh, yeah.